team of astronomers has zeroed in on a long-theorized supermassive black hole at the heart of the Milky Way and produced its first picture. The gentle giant, as it has been described, has over long periods devoured the equivalent of 4 million suns, whose only remnants are their gravity and a brutalized space time. The announcement by the US National Science Foundation, along with the Event Horizon Telescope collaboration in Washington, answers a greatly debated theory that the object known as Sag star or Sagittarius A star is indeed a black hole. Located 27,000 light years from Earth, the data from the black hole took those many years traveling at the speed of light of about 6 trillion miles a year. The distance works out to be a staggeringly incomprehensible 162,000 trillion miles. To explain what it means to find the much speculated black hole at the heart of our home galaxy, I speak to Professor Feryal Özel of the Departments of Astronomy and Physics at the University of Arizona on Mayanchai Reports. Apart from the prediction in Einstein's theory of relativity in 1905, in 1931, a 21-year-old Subramanian Chandrasekhar calculated that if a star is big enough when its fuel runs out, there is nothing to stop gravity from making its core collapse and in the process create a black hole. It's about a little more than a century now. And you've looked at two images, one from the M87 and the other from the Milky Way. As an astrophysicist, what was your first reaction?
It is fantastic to see a mathematical prediction come to fruition when we actually gather astrophysical data and we interpret it in the context of the most sophisticated models. And what we see is that there is indeed a way for nature to form these, what we're calling black holes, these singularities, these infinite energy density, where gravitational collapse wins, and there is nothing that can stop it. So we still think and hope that 100 years after Einstein's theory, that something will be different once this collapse starts happening, and maybe there is going to be some sort of modification to the theory, some deviation, but right now we're not seeing any evidence of that. So we're both super happy and a little anxious to see something maybe in other data sets.
What are the dimensions of the Sagittarius A? How big is it?
Sagittarius A is small in the sense that when we talk about supermassive black holes, they can be anywhere from 1,000,000 times the mass of our sun to 10 billion times the mass of our sun. Sagittarius A star, in terms of just its mass, is on the smaller side. It's 4 million times the mass of our sun. So but of course, that's still a lot of mass, right? I mean, it's just millions of times the entire solar system. But when you think of the physical dimensions of its horizon, that point where even light can't escape, that point of no return, it's smaller than the orbit of Mercury. So we're taking 4 million times the mass of our sun, squeezing it down to a volume that is smaller than the orbit of our inner planet. So it's mind-boggling.
It is, yes. As large and powerful as supermassive black holes are, is there a quantifiable intragalactic impact they have from, say, a distance of 27,000 light years that we are? How do we feel its presence apart from looking for it and finding it the way you did?
That's a great question, because black holes go through various activity levels depending on their environment and how much gas is available to them to grow on. They go through active phases that we call quasars, where a lot of stars are forming around them, a lot of gas is available, so it's coming down at a fast rate. And in return, of course, there's a lot of light that is being produced, again, not from the black hole. The black hole never produces light, but this hot gas swirling around it en route to the black hole shines very brightly. During those phases, they have a huge impact on their environment. Sometimes there are also jets that just jut out from this heart of activity, and there can be just these powerful jets blowing away the gas. It can shut off the formation of future stars. So there is a real give and take between this galaxy's central supermassive black hole and the galaxy itself. Ours is in a quiescent stage right now. There isn't that much happening around it. So we can still infer its presence by turning our telescopes to it. It was discovered as a radio source, and then we realized, oh, it also emits X-rays. It emits a little bit of infrared light, but it's pretty dormant. It's just eating. Of course, it's an anthropomorphism, but it's gathering, because of its gravity, some gas from the nearby stars, but it's not a very active period.
Right. I want to quickly digress before I come back to the main theme. Gravitational waves, which we saw when two black holes collided.
Yes.
Can a single black hole create any kind of ripples at all? And if it can be detected here?
Single black holes don't create the ripples that we can detect at any point. So what does happen is that as material accumulates, the space-time of the black hole changes a little bit in response to it. But these are extremely minuscule changes compared to the types of space-time deviations that we're sensitive to. It is really when two black holes, or a black hole and a neutron star, coalesce towards one another that it creates these larger ripples that we can detect.
The first hints of the Sagittarius A were sometime in the 1970s. It's we are getting into about 50 years after the first hints. How is it that the science of astronomy is able to sustain its work for such a long period of time?
It's not a continuous effort. It comes in bursts, and it shifts focus from the earliest detection of a source, trying to characterize it, trying to figure out what could this be, those early models, to, for example, the work of a couple of decades of following the motions of stars around it by two groups, one at UCLA, one at the Max Planck Institute in Germany, trying to gather more and more information about its characteristics through these detailed observations, to the Event Horizon Telescope, which itself is a nearly 20-year-old project from its inception, but really took a lot of effort in the last 10 years, both outfitting our telescopes and developing our algorithmic tools and theoretical methods to make use of those data. So it is true, it's 50 years from, oh, there's a radio source there, towards the constellation Sagittarius. That's where its name comes from. To, all of these intermediate observations of trying to understand what it does, and then finally obtaining a direct image of it.
Right. Why is it that most galaxies have supermassive black holes at their center? I mean, couldn't they be elsewhere and still be making the kind of impact that they do?
Well, they're the most massive component of the galaxy. So through gravitational interactions, they go towards the center. So even if at some point in the lifetime of the early galaxy, what we call the proto-galaxy, they formed somewhere else, the most massive black hole was someplace else, and then it kept on merging with its neighbors, it kept on growing, it will eventually sink to the center. Sink being, of course, the gravitational equivalent of what we experience on Earth towards the bottom.
Related to that is how the galaxies without supermassive black holes, how are they different?
Well, the only time we don't definitively see a supermassive black hole at the center of a galaxy is if it's a very small galaxy. So we are not sure that we have the complete sampling of all supermassive black holes in galaxies, but you could imagine a case where the galaxy is so small that we call those dwarf galaxies, that it doesn't hold on to enough gas to form sufficient number of stars, a black hole, etc. So apart from that, we basically see a black hole everywhere we look, every galaxy that we look at.
I see. So do I take it that it is inevitable for a regular sized galaxy to have a supermassive black hole?
It seems that way.
Okay.
I can't prove that statement because we, as the astronomy community, haven't really looked at every galaxy and definitively showed that there is a black hole, but that certainly seems to be the trend in our data sets.
In terms of any galaxy, say if the Milky Way or even M87, what is the real purpose of a supermassive black hole? Does it power anything? What does it do?
Well, I think it's sort of like we were just saying, it's sort of inevitable that they form. There are massive, very massive stars where when they run out of fuel, they're at the end of their lifetimes. Sometimes they can have an explosion, sometimes they don't even have a full-blown supernova explosion, and they implode onto themselves. And if there is no other force that can counter the effects of gravity, they collapse into these objects that become black holes. And over time, if there is material available around them, they're going to keep growing. If they encounter another black hole, they're going to do their little dance that LIGO sees and then merge into a new one that's bigger. So it's just basically the arrow of time kind of takes us in the direction of forming these black holes and then making them big at the centers of galaxies.
Right. Now, perhaps it's naive of me to think this way, but say, for instance, in the context of our solar system, at the heart is the sun, which essentially fuels everything.
Right.
If there is something at the heart of anything, it will have a purpose which is just larger than just it being there, right? That's the standpoint from where I'm coming.
I understand. I think in astrophysics we tend not to think of a purpose,
Right.
but of like once it's there, what is the impact and what is what could it do to its surroundings? And black holes do seem to regulate what happens, at least at the centers of galaxies. So in terms of controlling the fate of a galaxy, they certainly play an active role. But I'm not sure if that's like if they would feel that's their purpose. They just exist, and they can go through these powerful phases where they're the boss.
Right. I'll come back to the philosophical question of purpose in a bit, but something like the Sagittarius A, I'm trying to understand how far its impact is felt from its event horizon. Say I'm 5,000 light years away from it, or 1,000 light years away, whatever the distance. At what point would I begin to feel that there is a presence of a supermassive black hole?
You need to be fairly close. Even the stars that we follow orbiting around them by astronomical standards, meaning the galaxy standards, they're pretty close. Probably inner thousandth of the galaxy. Outside of that, you wouldn't know that it's there. It's not like you're destined to go towards the central black hole. I think it's a matter of when are you gravitationally feeling the impacts of that versus everything else that's around you, stars, the disk of the galaxy, the dark matter, and everything else.
Right. We are about 27,000 light years away from it at about 6 trillion miles a year. The light covers about 162,000 trillion miles. Now, this is a staggeringly incomprehensible figure for most people. How do you, as a scientist, keep up the scale and have people interested in it, is it not detrimental? Because I think people lose you at perhaps 5 miles. They cannot.
Well, astronomers have this amazing trick. We redefine units to things that sound smaller. For example, the distance of our our galactic center is only about 8 kiloparsecs from us.
Right.
So when you say kiloparsec and no one knows what that unit is, you're like, oh, it's just 8 kiloparsecs. So of course, I'm joking. But
Yes.
when you start thinking about astronomical objects, you have to use units that are innate to that environment. So our galaxies, for example, about 20 kiloparsecs across.
Right.
So if you're talking about things the size of a galaxy, you're right. The distances in a city, or even the distance from here to the moon or to our sun, start not making that much sense because we're a small self-contained stellar system. So you need to go to a scale where, oh, that's a galaxy, oh, that's the distance between galaxies, etc.
Right.
So I know that in terms of impact on our daily lives, it might feel remote, but when you're trying to understand the universe, you have to be able to take a look at it from some distance and say, well, this is how I'm formulating it all.
Right. The M87 black hole is about 55 million light years from us.
Yeah.
And yet its image seems as resolved as that of the Sagittarius A, which is 27,000 light years, as we discussed. Why is it that?
Almost. You're absolutely right. Their images are almost as resolved as one another, with Sagittarius A star having somewhat more resolution. The reason is that the black hole at the center of the M87 galaxy, which is an elliptical galaxy in the Virgo cluster at the distance that you just mentioned, it's much more massive. And the horizon, according to Einstein's theory of gravity, the horizon of a black hole scales with its mass. So the more the mass, the physical size of the horizon is bigger. So M87 is 1,500 times more massive than Sagittarius A star. Instead of being 4 million solar masses, it's 6 billion solar masses. So that just makes the image bigger in the sky, but then you put it 2,000 times further away. So 1,500 and 2,000 almost cancel one another. It ends up being a little bit smaller as an angular size in the sky.
I see. It has taken over 300 researchers and 80 international institutions and 8 telescopes, if I may add, to arrive at this image of the Sagittarius A. How was the coordination done among such a wide diversity of scientists and institutions?
It took a lot of effort, and the Event Horizon Telescope collaboration is a grassroots effort. What I mean by that is there isn't one funding source that trickles down to all of us that gets distributed and one management structure. So we really had to work hard on bringing our individual funding from various agencies, depending on the countries that we belong to. We had to work hard on an organization structure where we could divide up the science topics. The initial project project scientist is credited for just setting up all of that structure, and then really having some governing bodies like a management team and a science council to really work through all of the kinks that we encountered along the way. I can't say that it was easy. It is a co-op. Right. We know that we all need to work together, and we made it work because we wanted to.
Right. From what I gather, only 1 in 10 billion photons of visible light can reach us from the Sagittarius A. What odds, with odds like that, what were the challenges for the EHTs?
So, of course, light goes in every direction from a central source. We do, let me correct myself. We do encounter astronomical sources where it's more like a flashlight, where it's more beamed. But Sagittarius A star isn't like that. It emits in all directions. It sends light in all directions. So by the time you're at the distance that we're at, of course, we're collecting only a little bit with our telescopes that are big for us, but really small in astronomical scales. So it is intrinsically a faint source because it's a black hole and because it can't emit light very efficiently. Just the characteristics of the gas around it are such that it doesn't produce a lot of light, and then it gets diluted by that much by the time you get here. So it is really a faint source, which means that we needed both some collecting area in telescopes. We used arrays like the ALMA, the Atacama Large Millimeter Array in the Atacama Desert. The advantage of that is it has a lot of radio dishes that we are able to use simultaneously to collect that light. But then we added to that different radio telescopes elsewhere on Earth to be able to collect both light and the resolution information.
Right.
So that's what it took.
Right. What is the Schwarzschild radius of the SDRA?
Of the EHT array?
Yeah, the Sagittarius A, yes.
Oh, of Sagittarius A. It is comparable to the orbit of Mercury.
I see. Okay.
Yeah. So it's actually a little bit smaller because light that is produced around a black hole experiences an effect called gravitational lensing. It's just like looking through glass and seeing the rays of light bent around it, but there it's happening because of the strong gravity of the black hole. So we are seeing a little bit of enlargement because of that. When we say the horizon, we're really talking about this lensed horizon.
Right.
So horizon is a little smaller than the image size and still comparable to the inner solar system.
I see. I was thinking about the Hawking radiation and the lifespan of a black hole. Without the Hawking radiation, they would probably go on forever, in a manner of speaking. How, say, for instance, the Sagittarius A star, a black hole of that size, given the Hawking radiation, how long do you think it might last? It's a speculative question, but I'm curious about it.
So for Hawking radiation to be a net loss effect, matter needs to stop coming into the black hole.
I see.
Anything that it's able to accumulate from its surroundings is much more efficient than any loss of energy through Hawking radiation. So as long as it's gathering something, Hawking radiation is going to be negligible. Let's say that we get to a point where gas in all galaxies are depleted, or gas in the Milky Way is depleted. So Sagittarius A star truly is a source that turned off. Even then, it is many, many, many billions of years for Hawking radiation to cause an appreciable loss of mass from a black hole, including Sagittarius A star.
Do you ever wonder what there is inside of a black hole? Is it something touchable, tangible, physical? What is it, or is it just a void?
Of course I wonder, but our theories break down there. I think that's one of our frustrations with it, that it says matter as we know it, any characteristics as we know it, stops existing, and it's just a form of energy. Not just a form of energy, but all of that energy is concentrated in a singular point. So take all the mass that we've been talking about for either Sagittarius A star or M87, and you squeeze it down to a singular point, which means there, since you're taking something finite and squeezing it into nothing, things become infinite. That's the singularity that we refer to mathematically. And so not only does it stop existing in any form that we recognize, mathematically it bothers us too. So that's why we're thinking some modification to the theory of gravity, general relativity, needs to happen so that it becomes more compatible with how we describe subatomic particles through quantum mechanics.
Right. This is, of course, in the realm of sci-fi, but there are those who believe it's a gateway to something else. Is there even a remote scientific possibility that it may lead to a different realm altogether?
Not really.
Okay,
There are solutions that are called wormholes,
right.
but they're problematic. So we don't expect wormholes in the actual universe.
I see. Just last couple of things. One is, like I said, I'm curious always about the philosophical aspect of what scientists do. My background is physics, although I've been a journalist all my life.
Mhm.
Uh, the Nobel Prize winning physicist Steven Weinberg famously said, the more the universe seems comprehensible, the more it also seems pointless. I know you are not looking, as a scientist, looking for point or purpose to it, but I'm sure as a human being, you ruminate over I mean, look at the absurd scale of what we are in the midst of. If something of this scale just exists for the heck of it, it's difficult to wrap our heads around it, right?
Right. I hear what you're saying, and I think as a scientist, it is important to separate that from trying to find meaning in daily life because we are a speck of dust in
Right,
this universe, and trying to put meaning and goals and families and whatever else we deal with in life and love in real life in that scale, I think is uh, is challenging. So I I like very much working on it and trying to understand the workings of it, the physics behind it. How does this universe work? What is its scale? What are the laws governing black holes? But then I think I try to create meaning just personally in my own life, focusing on the here and now,
yeah,
and because otherwise it's true the scale of the universe makes it even harder, but scale of even the life on earth compared to a human lifetime
right.
makes it a little difficult to say I matter. But I think you set that aside and you're like here and now I'm trying to create something meaningful.
I see. And to conclude, since we are talking broader issues, where do you come down on the question of whether we live in a simulation? And the reason I'm asking is because if it is simulated, the scale of the universe that we are talking about, it may seem, but it's really not because it's a simulation. We will never know if you are simulated or not, but there is a serious school now that believes that we do live indeed in a simulation. Do you ever wonder about things like that?
I did when I was a kid. I think it's a thought that comes to one's mind when you're going through life and you're wondering how much you're doing something and how much it's controlled elsewhere. I don't seriously consider it. I think that we are able to, with our own minds, really find out how the universe works, even if we can't solve all aspects of it, even if we can't solve, not just in physics, but in biology and chemistry and all other disciplines, and astronomy, all aspects of it. I think that the human mind is capable of it. And human cooperation has shown time and again that something that seemed incomprehensible or unachievable eventually became so because we put our minds and
Right,
effort towards it.
right.
So I don't take that. I mean, like I said, it was a childhood thought for me, and now I'm happy to live in reality.
Okay, before I let you go, what is it? What is the latest thing that you're working on? I'm curious about if there is any paper that you're working on that you might want to share.
There are some papers in the works. We are already looking towards more analysis, different types of analysis of the data that we have from the
Mhm.
Event Horizon Telescope. There are also different types of analysis methods that we're developing to make our conclusions even more robust. Right now, I think we're just going to take a few days of a breather, just because it's been a very, very hectic few years. But yeah, there are things cooking, definitely, in terms of improving the images, improving the content, the science content of what we can learn from them. And then next year, we are gearing up towards hopefully doing these observations in a different wavelength, which is going to give us a whole new look at the black
I
holes
see.
and
I see.
combining the two.
I completely forgot to ask a question that was bothering me. What if there was a black hole of any size in the neighborhood of our solar system? And by that I mean 4 or 5 light years away, say Alpha Centauri, for instance.
We don't know of any. Of course, we look for black holes through many different techniques. Whenever they're active, if they're not just isolated, wandering around the galaxy without any sort of interaction with another star or another cloud of gas or anything like that, they're very hard to see because their sphere of influence isn't that large, as we mentioned
Right.
some minutes ago. So those are hard to find, but we turn telescopes to areas or regions that are near the solar system all the time. We look for them in X-rays, where you tend to first discover them. We look for them in the radio in case they do have properties that are like Sagittarius A star or M87. And we know of small black holes that are closer than Sagittarius A star, but even those are not very close to us.
On that note, Dr. Ozel, I want to thank you for your time. I thoroughly enjoyed it. I hope you did too. I will
Very much,
send,
thank you.
and excuse me if some of my questions were rather naive, but I'll have to do it to get readers to understand, they wrap their heads around it.
Absolutely. I'm happy with any sort of question as long as I can contribute to some understanding.